All right, well, again, it's u-substitution, which is going to be the important tool to obtain the integrals of secant and cosecant. So again, let's state the result first. So first of all, for secant, unfortunately, these are a little bit messier than the integrals for tangent and cotangent, and certainly messier than the nice simple integrals for sine and cosine, but that's all we can do. This one is equal to the natural log of the absolute value of secant x plus tan x plus c. So that sum is inside the absolute values. And then the result for cosecant, there's actually a couple of forms of this that you'll commonly see. You could write it as negative the natural log of the absolute value of cosecant plus cotangent plus c. So the same form in both cases, just this one gets the negative in front. But you can also manipulate that. I won't go through the algebra of doing it, but with a bit of work, you can show that if you'd prefer to have a positive coefficient here, then this means the same thing as the natural log of the absolute value of cosecant x minus cotangent x plus c. And again, you'll see both of these cited in different textbooks. It doesn't matter which one you use. They are completely equivalent. Obtaining these is both the integrals for secant and the integral for cosecant. They basically work the same way. So again, I'm only going to prove one of them. Let's prove the second one, just the first form of it. And this one, well, here it might seem natural again to rewrite cosecant as a quotient, because we know cosecant is 1 over sine, but at first glance that seems to be a bit of a non-starter, because, well, 1 over sine, that's not integrable by u-substitution. If we let u be sine x, du, of course, would be cosine x dx, and there is no cosine. So that suggests then that maybe that's not the right approach to take. Instead, we've got to find a different way, and frankly, it's a much less obvious way to rewrite cosecant. And this is not one of those things that you would necessarily just come up with off the top of your head. This is something that you use because it works. And when this result was first obtained, it probably took a whole bunch of different efforts to apply all kinds of different ways of rewriting cosecant before the correct method was identified. So for number 2 here, how we're going to do it is we're going to take cosecant x and we're going to multiply it by a very specific expression. We're going to multiply it by cosecant x plus cotangent x. And of course, we can't just multiply by some random expression, because then we're working with a completely different function. So if we're going to multiply that in, we also have to divide by the same thing, so that effectively we're multiplying by a very conveniently chosen form of the number 1. All right, so then in the numerator, that's going to give us cosecant squared plus cosecant x cotangent x. And then the denominator stays cosecant x plus cotan x. Now, that seems to make it so much worse. But in fact, that's the step we need in order to be able to use u-substitution. And so, of course, what this means is that the integral of cosecant x is the same thing as the integral of this now suddenly kind of grotesque expression. But now we can take the same approach that we did in the last proof. We're going to let u again be the denominator. So if I let u be cosecant x plus cotangent x, then du, the derivative of this expression, well, the derivative of cosecant x is negative cosecant x times cotangent x. The derivative of cotangent x is negative cosecant squared x. Of course, all of that is going to get multiplied by the differential dx. And well, compare this expression to this numerator. We've got a cosecant x times a cotangent x in both. We've got a cosecant squared in both. We do have an extra factor of -1, but that's okay, of course. We can pull that out and divide it across to the left-hand side. And if I'm going to do that, why don't I make these even more obviously similar? I'll just rearrange the order of these two terms so that it matches what I've got up here. And so then that'll tell me that negative du is cosecant squared x plus cosecant x cotangent x all times dx. So that means that the denominator here is our choice for u, and that whole big numerator times dx, all of that simply becomes negative du. So all of a sudden, that gets a lot simpler. So now we're going to have, well, the integral of cosecant x is now going to be the integral of, and that's just u, and all of that becomes negative du. So I can pull that negative outside. And again, I wind up with just the integral of 1 over u. We know that's the logarithm. So this is going to be negative the natural log of the absolute value of u plus c. And of course, we sub back in for u. So we get negative the natural log of the absolute value of cosecant x plus cotangent x plus c. So that's how that's done. And the integral for secant, again, works very, very similarly. In that case, we would take secant and we would multiply it by secant x plus tan x divided by secant x plus tan x. And everything works out the same way. The only difference is that we don't wind up with these negatives in the derivative. So that's why that's a positive logarithm. All right, so there we go. There's another result obtained from u-substitution, which means that now all 6 of our trigonometric functions, we've figured out how to integrate them. Which, hey, 2 sections into the course, add that to all the other properties that we've got. I think that's pretty good. Now that we've got u-substitution, though, and now that we've seen how we can use it to obtain a number of additional results, it's time to address one of the other unanswered questions from section 1.1. And that's about inverse trigonometric functions. I said there that I could have obtained a few additional common integrals using our knowledge of the derivatives of inverse trig functions, but that we were going to be better off holding onto those for a little while before we had something that could let us get more useful results, and that something is u-substitution. So in section 1.3, we're going to explore integrals that result in inverse trigonometric functions in a fair amount of detail. Let's start that in the next video.